Final example. So we've got two identical metal spheres fixed in place. So one here and another one here. At first, they have an attractive force on each other of 0.15 newtons. So we're going to assume gravity is not affecting this here. So the only thing attracting them is the force of electricity. So if they've got an attractive force, what's that mean about those charges? They've got to be opposite. We know Q1 and Q2 have to be opposite. One might be positive, one might be negative, or it might be negative and then positive, but we do know that they're not the same type. So at first they've got an attractive force of 0.15 newtons. They are then connected by a very thin wire, which will allow for conduction. So one of them has a bunch of positive charge, the other one has a bunch of negative charge. Remember, positive charge wants to get away from all of its other positive charge friends, and the negative charge, I guess I should say more enemies because they're trying to flee one another, and the negative charge is trying to get away from the other negatives. So they flee onto the other side, and we're going to get that they're going to add together. We're going to get that spread out. Since we've got identical metal spheres, we know that we're going to get identical spreading. So the final charge on each of them, Q final, QF, is going to be whatever was on Q1 plus whatever was on Q2 divided by 2. It's just going to be the average of those two charges because it's going to be evenly spread out. They're both going to have to get the average, otherwise we're not going to have even spreading. Notice that this means that we're going to have a pretty small amount of charge in the end because one of those was negative eventually. So that the total amount of charge, total net charge, is going to have to be less than what we had as the net charge on each of them originally. Okay, so the wire is removed, and we'll assume it's a very thin wire, so we don't have to worry about any real charge being taken away on that wire once it goes away, because there would be a few elementary charges strung along that, right? But we're going to assume it's so thin, so small, very few are going to wind up being left there. They're almost entirely going to be on the spheres. Finally, the spheres repel each other with a force of 0.03 newtons. If the charge on them is positive at the end, what were the initial charges? So at the end, we've got positive charge, so that means that we know QF is positive, and now we're ready to start working this out. So we've got that the distance between them is 0.7 meters, the initial force is negative 0.15 newtons. Now that's a really key thing to notice, is it isn't positive because it's attractive. Now, we haven't really talked about how we tell where, we've only talked in terms of magnitude. So a magnitude of negative 0.15 is the same as positive 0.15, but notice if we plug in Q1 as positive and Q2 as negative, or Q1 is negative and Q2 is positive, the important thing is they have opposite signs. If we plug in opposite signed charges, we're going to have to get a negative force from that formula, otherwise things are going to break. So an attractive force is always going to be given by a negative value. That's an important thing to keep in mind. An attractive force will be spit out when we get a negative value, and repulsive force will be spit out when we get a positive value. A little bit different than what we were working with gravity, where we always had attractive force because even though it always spit out positive. So it's an important thing to keep in mind. It's something that just sort of comes up because of the way we've talked about it. We never introduced some of the technology, some of the mathematical machinery necessary to skip this issue, but it's okay. Just remember that it's got to be negative if it's attracting, positive if it's repulsive, and that it's up to you to pay attention to where it's pointing based on how the problem is set up. All right, so if we've got this, then we know that we can figure out QF now, because force final is 0.03, a positive force because it's repulsive, Q final times Q final, right? Because it's Q final on both of them, divided by that distance squared. We solve for Q final, we'll get R squared 0.03 divided by K equals Q final squared. We take the square root of this, we plug in the numbers we've got, 0.7 squared times 0.03 divided by the electrostatic constant. Solve that out, and notice that since we took the square root of both sides, we could actually have plus minus, but we know for sure already this has to be a positive number because we were told that at the end the charges were positive on each sphere, right? So we know that Q final has to wind up being positive. So we've got 1.28 times 10 to the negative 6th coulombs. So that's what the final charge is. Now we can use that to work to figuring out what the initial charges were. Notice, if QF equals Q1 plus Q2 over 2, then we can solve for Q2 to plug it in. Okay, so let's look first at our initial force was negative 0.15 equals K Q1 Q2 over R squared. So to solve this equation, we're going to either have to get rid of Q2 or get rid of Q1. To do that, we use the fact that we know Q final is equal to Q1 plus Q2 over 2. So 2Q final equals Q1 plus Q2. So we can say Q2 equals 2Q final minus Q1. Now this isn't a problem anymore because we know what Q final is, right? So if we know what Q final is, we can throw that in down the road. So now we can just toss in what we've got, negative 0.15. Let's simplify this a little bit as we go. Move R squared, move that K. So we're going to have Q1 times what we sub in for Q2, which is 2Q final minus Q1. All right, we multiply that Q1 over. We get R squared, negative 0.15. Let's move that negative out front. Negative over K equals 2QF Q1 minus Q1 squared. All right, so at this point, we'll move everything over to one side because what we've got now is we've got a quadratic formula. I mean, we've got a quadratic equation at this point, right? We're going to have to use either the quadratic formula or some sort of calculator that has an impressive amount of algebraic solving in it. So we've got Q1 squared. We keep moving things over because we want to have this equal to 0, minus 2QF Q1 minus R squared 0.15 over K. Let's substitute in all the values we know, and it equals 0. We've got an equation here. So we substitute in all the values we know. Q1 squared minus 2Q final was 1.28 times 10 to the negative 6th. Q1 minus R squared, 0.7 squared, 0.15 over the electrostatic constant, 8.99 times 10 to the 9th equals 0. Now, this is pretty ugly. I'll be honest, it's not a very easy thing to solve, not very fast, not very quick. But we've got some squared number, we've got some other number in front of, we've got Q1 squared, some number in front of Q1 by itself, and then some constant. We can figure out what each one of these values is, and we could either plug it into the quadratic formula, or if you've got some sort of powerful calculator, you could use an algebraic solver on that calculator to solve this whole equation. If you do either one of those, you'll find out that the two possibilities for Q1 is equal to either negative 1.85 times 10 to the negative 6th coulombs, or positive 4.41 times 10 to the 6th, 10 to the negative 6th coulombs. So we've got two different possibilities here. So how do we know which one to choose? Well, one thing to notice is that we could have also done this another way, where we could have broken QF and we could have solved for Q1, and we could have gotten Q1 is equal to 2QF minus Q2. So they're symmetrical. So however we did this, one of them, this is going to be, one of those charges will be negative 1.85 times 10 to the negative 6, and the other one is going to be the other one. We don't know which charge was on which sphere, and we can't know that without getting a little more information, but we do know that the two charges are going to have to be positive 4.41 times 10 to the negative 6 coulombs and negative 1.85 times 10 to the negative 6 coulombs. All right, hope that made sense. Hope you've got a better understanding of how electricity works, and we've got a lot more to cover in it. All right, thanks. See you at Educator.com.